I'd like to start welcoming you to the 47th webinar of the Graduate Program in Physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the cameras and microphones turned off, except for the moment you're going to speak. Questions will be allowed after the webinar, unless otherwise requested by the speaker. The questions can be asked using the chat, both in this virtual room and in the YouTube. Today, we have the honor to listen to Professor Bernard Frederick Schutz, who is a Fellow of the Royal Society, of the Learned Society of Wales, of the US National Academy of Sciences, and of Germany's National Academy Leopoldina. Bernard Schutz was born in Paterson, New Jersey, in the United States of America, and came to Cardiff University in Wales as a lecturer in 1974, working on the astrophysics of relativistic systems like neutron stars and black holes, and on their gravitational wave emissions. From mid-1980s, he began to develop the theory underlying the techniques now used by LIGO and its partners Virgo and Kagra to find weak gravitational wave signals in their data. He moved to Germany in 1995 to help set up the Albert Einstein Institute, where he expanded his research in data analysis and numerical relativity. He returned to Cardiff in 2014 and helped to establish the Data Innovation Research Institute and became its first director. Professor Bernard Schutz has received various distinctions, among which I can mention, in 2006, the Amaldi Gold Medal of the Italian Society of General Relativity and Gravitation. In 2019, the Eddington Medal of the Royal Astronomical Society, and in 2020, the Richard Isaacson Award of the American Physical Society. Professor Schutz is known worldwide for his contribution to gravitational wave physics and also as the author of two vastly used textbooks, namely Geometrical Methods of Mathematical Physics, published in 1980 by Cambridge University Press, and a first course in general relativity, published in 1985, also by Cambridge University Press, as well as the book Gravity from the Ground Up, an introductory guide to gravity and general relativity. I should warn the audience that a new edition of the textbook, a first course in general relativity, is expected to appear later this year or early next year, for what we are all anxious to see published. In Germany, Professor Schutz has established the open access journal Living Reviews in Relativity, which has become the highest impact open access journal in the world, which is now published by Springer. The gravitational wave universe, our first view, is the theme of his webinar today. And I should not make you wait longer to listen to him. Professor Bernard Schutz, thank you once again very much for having accepted our invitation. And from this moment on, the audience is yours.
Oh, well, thank you very much for that very nice introduction. And it's a pleasure to be able to give this talk, the wonders of being able to give talks remotely that we've developed we've become accustomed to in the last couple of years, really does sometimes makes it a good way of doing science, although I'm sure that other aspects of the pandemic have slowed us down tremendously. But it's a pleasure to be able to give this talk. The background of this, of course, is that we made the first detection of gravitational waves in 2015, and that was our very first view of what is sometimes called the dark side of the universe. But we're just beginning, and so what I intend to do in this talk is first to give you a little bit of a review of gravitational waves. I'm sure some of you are very well versed in it, others not so much probably, and then talk about that first detection and other ones that we've made since that first one, and the progress that's been made in the sensitivity of our detectors. And then I'll finish with a view ahead, because this is a growing, expanding science, and we've raised more questions with these first observations than we can answer, and so we're going to be looking for the answers and looking for new questions as soon as we can turn our detectors back on. So here we go. First, gravitational waves and Einstein's theory. This is a very elementary kind of introduction. The picture here is something that the LIGO team put together to illustrate what was going on in that very first detection, the spiral of two black holes that got closer and closer together in their circular orbit. Finally, they merged together and formed a single black hole that very quickly became stationary after what we call the ring down phase, where it radiates away in gravitational waves all of its non-smooth configuration that you would have when you first form the horizon. So gravitational waves, start with some simple facts. First of all, there is a lot of analogy between electromagnetism and gravitational radiation, electromagnetic waves and gravitational waves. But there are also contrasts. They both travel at the speed of light. They both have, you know, origin in some sort of electromagnetism. It's charge, and gravitational waves at the lowest order anyway, it's mass, but it's mass energy. And also in electromagnetism, you know, it's not just charge, but it's also current. And in general relativity, that's a consequence of special relativity, that it's not just mass and energy, but it's also momentum. And it will also be stress and pressure and so on, can give rise to gravitational effects. At the lowest order, in a relativistic expansion, in other words, for slow motion sources, in electromagnetism, radiation is dipole. There's no monopole radiation because of charge conservation. In general relativity, there are two conservation laws, not just the mass would be the analog of charge, but also momentum is a conserved quantity in physics, and that eliminates not just the monopole, but also the dipole radiation. So the lowest order radiation in general relativity is at the quadrupole level. When we do general relativity, it simplifies things to use units where c equals g equals 1, and that's because the units that we have in the standard SI system were not developed to deal with black holes. They have arbitrary sizes. Basically, the standards are human standards, not natural standards, and so we can go some way to simplifying the equations by setting c and g equal to 1. And of course, the conversion factor for mass, for example, would be to multiply a mass in kilograms by g over c squared to get the mass in units of length in meters. And so typically we use meters as the one remaining unit. When you do set c equal to 1, then all velocities are dimensionless, and the Newtonian potential has units of velocity, velocity squared, and so it becomes dimensionless as well. And that's important because there's a very simple formula for the maximum amplitude of a gravitational wave if you're dealing with the quadrupole radiation, that is the lowest order in a low velocity situation, and also with Newtonian sources, with stars going around in well separated in orbits, let's say. That maximum amplitude, which we call h, and I'll explain what h is in a minute, is the product of two Newtonian potentials. One is the internal potential, that is the typical potential within the system, which is doing the radiating, and the other is the external potential, which is basically m over r, the mass of the system that's doing the radiating, divided by the distance. That's a very simple formula, and it actually works well for the gravitational wave amplitude of a binary system, and that's because with a binary system you have all mass is in the quadrupole moment. There's nothing else in the system. It's just two masses that are opposed to each other in an orbit. So if you have two masses, particularly if they're equal, then then you get very close to that upper limit. Again, staying on simple formulas, the luminosity, the energy luminosity in gravitational waves of a binary system is the 5th power of its internal potential, a typical value of the internal potential. This is scale-free. You see, that's dimensionless. Luminosity is dimensionless in these units. You want to go back to watts or something like that, you multiply by c to the 5th over g. And that has, the number c to the 5th over g has units of energy per unit time, watts, let's say. So luminosity is dimensionless in general relativity, and that indicates that it's scale-free. There's no mass scale. So a binary system with the same internal potential, whether it's composed of 2 massive black holes or 2 tiny black holes, they would have to have different separations in the 2 different cases in order to get their potentials to be the same. But if their potentials were the same, they'd be radiating with the same luminosity. Gravitational waves are weak and strong at the same time. The weakness is famous because our detectors had to be made extraordinarily sensitive. This amplitude that I've been talking about at gravitational waves, which is a dimensionless number, it has to be, I gave you the upper bound, and the upper bound was the product of the 2 potentials, but certainly therefore, since the internal potential is going to be less than 1, the wave is going to be a small fraction of its external potential, which is gm over r, or gm over r c squared in this, as it's written here. And that leads to h being of order, if you put in typical masses and typical distances for things that you might be interested in, of order 10 to the minus 21 to 10 to the minus 24. We'll see in a minute that h is the strain, the relative change in the size of our interferometers. That's what we're trying to detect. Very, very small. And of course, it folds up as 1 over r, so it gets smaller as it gets further away. This weakness is good because it means that gravitational waves are almost perfect messengers. There's negligible absorption or scattering because they just interact with matter between the source and us with this amplitude of 10 to the minus 21. So any effect on them is 10 to the minus 21 of the gravitational wave itself. So there's negligible scattering and absorption. But it's also the case that although the amplitudes are small, the energy fluxes are huge, and you should understand this. It's a very important thing to understand about gravitational waves, that the energies being radiated are enormous. And there's a good reason for this that I think you can understand. It's an analogy that my friend and colleague Carsten Donsman has made, which is that when you have a solid material that's carrying vibrations, think of a bar of steel or a piece of wood. The stiffness of the material affects the speed. The faster the speed of the vibrations are carried, the stiffer the material. But also, it affects how hard it is to bend the material. What is the amplitude associated with those vibrations? A bar of steel will have very fast waves with my headphones suggest I've dropped out a minute, so I'll start again. The energy that's being carried by the waves is distributed through the bar in compression of this material, which is very hard to compress. So the compressions are very small, the amplitudes are very small. Now, if you think about gravitational waves, they are ripples in space, and space must be the stiffest material at all because it has these ripples traveling at the speed of light, which is the fastest that anything can travel. And so in this analogy, you'll have the smallest amplitudes and the highest energies that are required to support even those very tiny amplitudes. So when you do the calculation, and again, it's an order of magnitude calculation, which is not hard to do if you put in luminosity and so on, you get the equations at the bottom, for example, for the energy flux carried by a wave. And if you scale that to things that are meaningful, for an amplitude of 10 to the minus 22 and a frequency of a wave of 1 kilohertz, which are typical of things that we do detect, the flux is 3 milliwatts per square meter. Now, 3 milliwatts per square meter isn't something like 10 to the minus 21. It's a real human scale energy. It's actually comparable to the brightness of a crescent moon in the sky. Your eyes are receiving 3 milliwatts per square meter when you look at the moon. So that's a huge energy, considering that it's been coming across the universe over billions and billions of light years. So the energy carried by the waves and the energy lost by the systems is enormous. And these are the most energetic events that we've been seeing. These are the most energetic events in the universe. This luminosity scale, the c to the 5th over g that I mentioned before, 3.6 times 10 to the 59 ergs per second, well, that's 10 to the 5 solar masses of energy per second. Black hole mergers get up close to that, okay? The merger of two black holes, and again, it's scale free, so it doesn't depend upon the masses of the black holes. They will peak out at luminosity on that scale, maybe a factor of 100 down. But that's an enormous amount of energy that they're radiating. So it's important to bear in mind that what we're looking for with the sensitive detectors are some of the most dramatic events in the universe. Now, we detect these with interferometers. The top line is a polarization diagram. You may have seen something like this before. What we have in the dots, you read the two arrays of dots horizontally. So let's just look at the top strip. The dots are meant to be free masses in outer space. The little dotted lines just show the array that they form. They're not connections. Those are free masses. And they're tidally distorted by a gravitational wave that passes from above, because gravitational waves act transversely to their direction, just as electromagnetic waves do. And so a wave coming above will turn that circle into an ellipse, and back into a circle, we're going across the top line, and into an ellipse with the same semi-major and minor axis orientations, but with major and minor reversed, and then back into an ellipse, back into a circle. And the amplitude of the wave that could produce the distortion that is shown there, which is visible to the naked eye, is shown in that by that curve. It's half the amplitude goes up to about 0.2. So the amplitude peaks at about 0.4. That's not 10 to the minus 21. The real wave will have 10 to the minus 21, but will have a similar effect, but scaled down, of course. The bottom strip going horizontally is the orthogonal polarization. And what happens is that the ellipse is rotated by 45 degrees. Instead of in electromagnetism having the orthogonal polarization being rotated by 90 degrees, in relativity and gravitational waves it's 45 degrees. Those two polarizations fully describe any gravitational wave, the superposition of those two. Now, if we look at the bottom of the picture, there's a schematic of a very simple array of an interferometer. You have light coming in where the lambda is from the left. It goes through a beam splitter to the two different mirrors and goes out. Well, the interference pattern anyway goes out down to the bottom where phi is equal to 0 if the interferometer is arrayed in such a way that the two arms are exactly equal. Now, when the gravitational wave passes, if the mirrors are free to move and follow this pattern, then you can get an ellipse, and therefore the mirror on the vertical, the y-axis there will come in, and on the x-axis will go out. And so that will create an interference pattern going out down to the bottom that's proportional to the that's affected by the distortion delta L, and allows you to measure it. And then half a phase of the wave later, when the distortion goes the other way, then you'll be having the y-axis bigger and the x-axis smaller. So you'll able to follow by looking at the phase of the light coming out at the bottom, you'll be able to follow the phase of the gravitational wave, and that's very important. The bottom row of the polarization diagram does not affect this interferometer at all, the way things are oriented. It tries to stretch at 45 degrees, and it'll affect both mirrors equally. In fact, it'll leave both mirrors alone. That's a node of that pattern. And so these interferometers are all linearly polarized detectors, okay? So that's an important thing, because we want to get information from the polarization. The other thing about this polarization diagram is that the dots, I've described them as being test particles that record the gravitational waves. They also can be thought of as the image of the source of the gravitational wave projected on the sky, because the way the source moves is translated directly into these tidal forces that are produced, that are carried by the gravitational wave. So if you have, for example, a binary system that you're looking at on the sky, and you happen to be in the plane of the binary, then you just have two stars that are going like projected on the sky. They're going like this. You don't know anything about the distance toward you. You only know the transverseness, and that produces this pattern, this plus polarization pattern, and none of the bottom. On the other hand, if you're looking down the axis, if the plane contains the orbit, then what you get is effectively you get a circularly polarized gravitational wave with both of these polarizations present in it, separated by an appropriate phase. And so if you can measure the polarization of the gravitational waves, then you can measure the inclination of the binary system that's doing the radiating. And that's something that we try to measure, because we try to do that with a network of detectors. Okay, so let's go on. Detectors measure the wave amplitude and the phase, and I described that before, because they're not measuring energy directly, and there's a lot of information in the phase. This is different from optical observing, where you're counting photons and you're only getting energy. Here you got the phase. Binaries radiate anisotropically. I've talked about that by measuring the orientation, but the radiation going up the axis, because it contains both polarizations, is twice as strong as that goes out in the horizontal plane of the binary. And so that means that there's a bias in the systems we detect, because we're always limited by the strength of the waves. So we'll see preferentially more face-on systems than systems in the plane. That's called a Malmquist bias by observers. We don't just have quadrupole. The multipoles beyond the quadrupole have been observed in some detections, and they radiate with different antenna patterns from the system. They provide even more information about the inclination. Now there's a notation or a definition that I want to introduce, which is the range for detecting. The way we measure our sensitivity in these detectors, we assign a range to detecting binary neutron stars. And binary neutron stars are a classic system, and we used to think, but we don't anymore, but we used to think that all the neutron stars would be about 1.4 solar masses, so it'd be a kind of a standard system. So if we could just say how far could we detect a binary neutron star averaged over the sky, let's say, then that would give us a measure of our range. Of course, other systems, massive black holes, we can see further away, so it doesn't mean that it's the actual range, but it allows us to compare different configurations and compare our sensitivity progress by tracking this fiducial range. So in 2015, LIGO's range was 60 to 80 megaparsecs for binary neutron stars. And in 04, the Observing Around 4, which is going to start next year, we expect that range to be 165 to 190. That illustrates the technical progress that there's been in the meantime. We do an observation run, then we shut down and we improve things. And so we've improved the range. We will have improved the range rather dramatically. If you look at volume, the volume is the cube of the range. And so it turns out that the detection volume has doubled on the average every 2 years since our first detection. And that means that the source rates, the number of systems that we detect, is doubling every couple of years. And that is likely to continue with the plans that we have for better detectors. I talked about averaging things over the sky, and that's because our antenna pattern, our detection pattern, isn't isotropic. The pattern shown on the left illustrates the detection pattern of the current detectors, the two LIGO detectors in the US and Virgo in Italy. The vertical direction of this diagram is geographic north on the Earth, and we're looking down on the Earth, down on these detectors from somewhere above the North Atlantic Ocean. And so you can see that there's directions in which our range is greater and directions in which our range isn't so good. So these, that means we're missing sources that might be close to us just because they happen to pop off at a time when our sensitivity in that direction isn't very good. When we get 5 interferometers, and there's another one, COGRA, has just begun observing with us, and we're building a 5th detector, LIGO India. When we have those 5 detectors, it rounds off the antenna pattern. We get the one on the right, and so we get a much more isotropic view. So that will double, just by itself, that will double the event, the number of events, even when you don't add in extra sensitivities and things like that. So what we're going to be observing is the polarization of the waves, as I've talked about, the intrinsic amplitude, the phase evolution. The direction to the source comes from the phase delays among detectors. The detectors are clearly not telescopes that point in a direction. I've shown you their antenna patterns. So what we do get is a wave will arrive at one detector before another, and so we get these phase delays that allow us to triangulate positions in the sky, but they're not all that accurate. We observe the phase evolution, and that gives us a huge amount of information. And one of them is we get the distance to the source from that. And that's a very unusual thing in astronomy, to be able to measure the distance to a class of objects. Those astronomers call them standard candles, and they're treasured because they set the scale for measuring distances to all other things. So it turns out that binary systems in general relativity are standard candles, or we call them standard sirens, because we're detecting something that's more like sound than like light. And what we get from measuring the amplitudes and the phases is the luminosity distance, DL. We also get a measure of the masses, which is called the chirp mass, M. The formulas there illustrate what we use. There's a characteristic time for the orbit to evolve, and what's very important here is that the orbits are shrinking because of the emission of gravitational waves. So F over F dot, the frequency is increasing as they shrink. So F over F dot gives you characteristic time. We call that the chirp time. The luminosity distance is proportional to that combination of things, C over the frequency squared, the chirp time, and the amplitude. And the proportionality depends upon angular things, depends upon where on the sky relative to your detectors. What is the inclination of the orbit of the radiating binary, because as we've seen, the radiation is stronger in some directions than in others. So we have to have all those angular things, and we get that all by measuring this with a network of at least 3 detectors. And then there's this combination of masses called the chirp mass is given there. It's an unusual combination. It's not a mass that turns up in any other part of physics, as far as I know. And we measure it through measuring the frequency and the rate of change of the frequency with that combination that's shown there. The chirp mass is a kind of magical thing. If you just count what are the unknowns for a binary system, and what can you measure from the strength of the signal, let's say a quadrupole radiation, a Newtonian orbit, and so on. What is there you can measure, and what are the unknowns? You can't measure, you can't determine all the unknowns. You can't determine in particular the 2 masses. But it turns out in this system that the 2 masses combine in this chirp mass. They're not independent. There's only one mass that actually enters both the formula for the amplitude that's being produced and the formula for the rate of change of the frequency, how the frequency changes. There's only one mass, and that collapse of those 2 parameters into one allows the system to be determined and allows you to measure the distance. And that's kind of magical, but it does come in a fundamental way from the scale-free nature of gravity. And that would be a different lecture, but it's a very fundamental aspect of general relativity, that we can make these measurements. And so if we want the individual masses, which of course we do, we don't get them from the basic lowest order radiation formulas, but we do if we go to one step up in the post-Newtonian expansion for the orbit behavior. So if we observe over several cycles, then we can see that the phase is evolving through the post-Newtonian formulas rather than if we can pick those things up, then we can separate the masses into their individual masses, but they're not well determined. So the chirp mass can be very well determined, and the individual masses will still have big errors because they're a post-Newtonian measurement, not the lowest order Newtonian measurement. The great thing about this distance ladder is we don't have any, about this distance, we don't have any distance ladder. We don't have to calibrate things. We don't have to understand complicated physical systems like stars and pulsating stars or giant stars or model lenses or something like that. We simply have to know how our detector, we have to calibrate our detector, we have to know how accurate our detector is, but we have a very clean model of a binary system, well separated for the period of the in-spiral that we're measuring and fitting these numbers from. The tidal effects are not important for measuring these numbers and all of that. So it's a very clean system, easy to model. This is in principle a very powerful way of measuring distances through the universe. And so it underlies everything, almost all the science that LIGO publishes. For example, the redshifts of things are inferred from their luminosity distance. We know what their distance is. Then we go to the formulas for cosmology, and we deduce what the redshift should be, because the redshift doesn't come out from the measurement. Everything is scale free. The cosmological redshift will redshift the frequencies or the rate of change of frequency in an appropriate way. And so all of these things come out in what I mean is there's no intrinsic way of measuring the redshift from the signal, unlike having an optical system with a line that you know what its rest wavelength is. There's no such thing in binaries. So we have to infer the redshift by knowing what the luminosity distance is. And we also then infer the local frame masses. The masses are redshifted So we have to go back to the local frame once we know the redshift and tell you what the real masses were, and population estimates, evolution estimates, or all of that, and of course measuring the Hubble constant, which is something I want to come back to. Well, I've taken a lot of time to talk about the basics of the relativity, but I certainly wanted to introduce you to our observations, and we've done 3 observation runs, 01, 02, and 03, and these graphs show the binary neutron star range of 01 and during 01 and 02. And the vertical is the scale in megaparsecs. I talked about these numbers before. You see that and the range didn't change very much between 01 and 02. There were some problems, and in fact, the red trace is the Hanford detector of LIGO has had a problem. One of its mirrors developed a defect, and that limited the sensitivity of the detector. That will be fixed for 04 for the next observing run, but it affected all 3 observing runs, well, the second and the third. You see a little bit of a purple trace at the bottom. That's when Virgo finally joined. Virgo wasn't present in 01 and joined at the end of 02 with a smaller range, and its range has been increasing as well. Virgo started later as a project than LIGO and is still catching up. The 03 has a much better range. You see Livingston detectors out at 140. So 03 has seen a big expansion of the volume and a big increase in the number of events that we've detected. So in 03, just the first 6 months of 03, which we call 03A, we have 39 events. And 03B is still being analyzed, and we're going to publish that catalog soon. But what I'm going to be talking about is up to 03A. This first event, and I'm sure all of you were aware of it when it happened, GW 150914. That's the trace. The picture shows the trace of the 2 detectors superimposed with a time shift allowed for, because it arrived at one detector before the other. So that's been removed. And the 2 signals superimposed within, of course, the noise extremely well. And they're above the noise. This isn't a highly filtered picture. There's a low pass filter and a high pass filter, but we're not filtering to knowing the signal at all. So it was an extremely strong signal. It tells us that the black holes were much heavier. Also, the signal finished. The horizontal scale is time, but the frequency of the signal at the end wasn't very high. It was in the 300 hertz range. We had been expecting much higher frequencies than that. The lower the frequency, the higher the mass. That's part of the scaling of general relativity. And so this told us immediately we were dealing with something with much heavier than we had expected. They were black holes, not neutron stars, and they were even heavier than the black holes that we had been seen in X-ray astronomy. So we were surprised at how heavy these black holes were. And that made us worry, because it arrived even before 01 began. So 01 was about to begin, scheduled to begin a week later. Engineers have been in the detector buildings during the day, but they, according to protocol, they had shut when they left. They had locked the doors and turned the system back into observing mode. And so this thing arrived overnight before 01 was to start with signal we didn't expect and much stronger. So was that nature being generous to us, or had we been hacked? Was there somebody who didn't like gravitational waves and all the money had been spent on these detectors and wanted to embarrass us into making a false claim? That was our first worry. And so we spent a month. We assembled a team that really knew the detectors, and they came back after that month and said, no, after all, there's thousands of data streams being recorded, not just this output. And to make everything self-consistent, a hacker would have had to know the ins and outs of the system, according to this team that we assembled, even better than they did. And so they had confidence this was real. So we retired that worry and we began to prepare the announcements, which happened on the 11th of February in 2016, with an amazing resonance. I wasn't really expecting the kind of reaction that this got, not just in the scientific community, but worldwide in newspapers and so on. And I think the thing as I'm proudest of is that PhysRev Letters website crashed for the first time ever because everybody was trying to download the open access paper. The next detection was at the end of December, and we then were very relieved because that any residual doubts that this was a fake vanished, that we had another detection and it was again rather massive, and we could explain it. The next one that several were notable, but the one that I really want to talk about, again, got all the headlines, which is the binary neutron star, the first binary neutron star detected, 1708-17. There had been time to upgrade the system, so we were in 02 now, and Virgo had just started. It was the end of 02, and that little purple trace in that other diagram, Virgo was involved, and that was great because if you look at this finding diagram on the sky, the light green is what the two LIGO detectors could pin it down to, where the location. But if you added in Virgo's information, then it got to be a much smaller ellipse on the sky. There was an associated gamma ray burst, but it didn't give very good position information. But the LIGO-Virgo combination pinned it down to an area that only had 100 or so large galaxies. And so teams began to search for it, and this was a finding diagram that shows the picture before and after. The bottom frame is a particular galaxy photographed 20.5 days before the event. The top frame is the same galaxy photographed 10.9 hours after the gravitational wave event, and you see there's something there, and that's the kilonova. And then everybody started looking at this system. What did we measure from the gravitational waves? The chirp mass was extremely well measured, but the two individual masses, as I said, were not. So this diagram shows that there's a range of masses possible, but the ones that are consistent with what we know about neutron stars, very consistent, are the blue ones. And that's the fit that you get if you assume that they're not spinning very fast, that there's rather low, moderate spin. So this was probably a simple binary system, much like we see among binary pulsars in our own galaxy. The distance we could infer was 43.8 megaparsecs. That was about 10% error. The error comes from not being able to determine the inclination very well. And that's because Virgo could contribute to the location, but not to the measurements of the polarizations. And so we couldn't separate the polarizations very well with the two LIGO instruments. They're almost polarized in exactly the same way, in fact. So this distance was, of course, important for the finding because we didn't have just an error circle on the sky. We had a depth, and that's why it was easy to find the event, find the counterpart. We looked for information about other things, but we didn't find very much information about the neutron star. We also don't know what happened to them. We assume it formed a protoneutron star of high mass, which eventually collapsed to a black hole itself, but we didn't see the gravitational radiation from that event. That would have been rather weak, that final collapse. But there was a lot of work among the optical and electromagnetic astronomers. The radio and the X-ray people looked at the jet, and they were able to pin down the inclination, which we were not so able to do with gravitational waves. The other thing I want to talk about, just mention, and we got a lot of publicity, is the R process elements. It had been known for a while that supernovae don't produce very many elements above iron 56. And it had been speculated that binary neutron star mergers do. And the lanthanide peak, the lanthanides were seen in the spectrum of this expanding cloud from the kilonova. to confirm this model. What got all the publicity in the newspapers was gold and silver. So if you're wearing a gold ring, that gold came from a binary neutron star merger sometime earlier than when the solar system was formed. But more important really for life is iodine, and even more important, I think, for life is uranium and thorium, which are radioactive. They're long-lived radioactive elements, isotopes, continue to keep the Earth warm. They distribute it through the Earth, and the heat leaking out from their decays seems to be crucial in allowing plate tectonics to happen, and it also is crucial in keeping the center of the Earth, the molten core, molten, and that molten core is what generates the Earth's magnetic field, and the magnetic field protects us from the solar wind, and that protects life, that allows life to exist on the Earth. So there's a very real sense in which binary neutron stars are along the path, our own world lines, way back before the sun was formed. There were binary neutron stars contributing essential things to us so that life itself could exist on Earth. We tried to measure the H0, and we got a value. I hope you realize that there's a big controversy going on right now. The Planck and the CMB measurements give a rather lower value than the standard candle measurements. We're using supernovae type 1A as standard candles. The left-hand diagram shows the Planck measurements in green and the standard candles in orange, and the posterior for our value, one measurement of H0, peaks nicely in between them, but is much too wide to be able to make a statement about which one we would prefer. And that width is partly, at least half of it is due to the inclination uncertainty that I talked about. So with only the gravitational wave data, we published a value of 69 for H0, plus with big errors, plus 22 minus 8. If you take now the inclination of 18 degrees that I mentioned was measured from the jet, that reduces the errors. It gives a very similar value to the peak one. It's very heartening, but it reduces the errors by a lot. And so that's a pretty good value of H0. It would have been very good 10 years ago. But it's still not good enough to say something about the discrepancy between these two things. But it shows what's possible. So I'll come back to that a bit later. If I give you an overview of Gravitational Wave Transient Catalog 2, which was published and contains the O3A events, and it's got these 39 events, and they're occurring so frequently that sometimes we get 2 on the same day. And so we can't just use our old nomenclature of just giving the date. So we give the date and the time now for all events once we realized we had to do that. There's some events about their own discovery papers. I'll talk about a couple of them here. But we've also been pushing boundaries. We've also been trying to answer questions or raise questions. And one is that 2 systems gave us one of the components, the minor component, with a mass between 2.5 and 5 solar masses. That's what we call the lower mass gap. That's higher than what a neutron star ought to be and lower than we think black holes should be able to form. So how did they get there? It's not impossible, but it's quite surprising that we have already 2 systems with objects, and we don't know if they're neutron stars or black holes. We also have objects in the upper mass gap, and I'll talk about this in more detail in a minute. But one of the primaries in the event 190521 has a mass around 90 solar masses, and that should not be able to form as a black hole. Black holes that would form with that mass are formed by stars with enough mass to undergo the pair instability, and they incinerate themselves. They don't leave behind anything. So how did that black hole form? Maybe it was formed from a pair of other black holes. Maybe it's itself a merger product, and we're seeing a hierarchical thing. Or maybe this happened inside a globular cluster, and it was formed by a merger, and then it acquired its companion later on through dynamical effects in the globular cluster. So there's questions, but no answers. We've also seen systems with big mass ratios, and that's a very interesting thing that I'll come back to. We've seen intermediate mass black holes form. We've seen so far 4 black holes formed by merger with masses above 100 solar masses. And there's a heavy system, and then there's the system that I said we don't know whether it's a neutron star or black hole. It's in that mass gap. One of the most interesting systems, individual systems, 1905-21. Here you have the traces from the 3 detectors. And what's notable about this is that you don't see many cycles. The peak of the trace is the merger. So time comes in. You just begin to see a few cycles above noise. Then there's the merger, and then there's a ring down. And so this is the fact that it's only a few cycles means that it's close to the bottom of our observing range in terms of frequency. It's a very low frequency, which means a very high mass. This is the one that has a component masses of 85. I called it 90 before, but there's uncertainties. 85 plus 66, and it formed an IMBH of around 150. It's our most distant source. Because it's so strong, we can see it far away, and we only get 4 cycles from it. The final mass actually was 142 because 8 solar masses of the total were radiated away. There was good evidence for precession and various other interesting details of the orbit. And here I want to point out that you can really see the ring down. You can see the black hole settling down into a curved black hole. And you would not see these particular cycles if it was one of the other exotic models for black holes that are supposed to replace black holes, that people worry about. Maybe we don't really see black holes, maybe we see gravastars or other kinds of things. But those dynamical systems have different dynamics, and these cycles fit perfectly what you expect for a ringing down curved black holes. So it's our best evidence that we really have black holes and not some substitute. There was also an optical flare from the system. Not from the system, it was detected by the Zwicky Transient Facility, which looks for supernovae. And it was 35 days later, but there's some possibility that it was associated, but that's something that's still speculative. I won't spend much time on it, but I do want to mention again the puzzle about the origin of these 2 stars. How could they have been formed in the mass gap before they finally merged to form this intermediate black hole? And then the other system I mentioned, which is 1908-14, is the one with a really high ratio of masses, 9-to-1. Which one of them, the primary is clearly a black hole. The secondary is probably a small black hole, maybe a neutron star. It's in the mass gap. We can't get an answer to that. But what's interesting is these higher mode systems, these high mass ratio systems also radiate more easily the high modes beyond the quadrupole, and so they give us extra information about the inclination. They give us therefore more accurate information about the distance, and therefore we can also use them as candidates for measuring the Hubble constant. And so we published a paper. We didn't get a very different answer. We got better error bar than we had before, only by a small amount. This is a picture that you may have seen at various times. This is the most recent update. All the blue things are our binary black holes and their product black holes, and the orange things at the bottom are neutron stars. We're fairly confident we have as neutron stars, and then their products, which we're not so confident about. So what do we learn? We learn about black holes, that they're much more abundant and they're much more massive than we had expected. We learn about their spins, and we learn about their sky positions. We learn about neutron stars. We are beginning to get information about the equation of state from the neutron star radius, that it's probably tending to be a stiff equation of state, and we'll get more information. We're learning the distances, as I've talked about, and we're getting H0. Now, these last 5 of 3 are things that benefit from statistics. And so as we go into 04, where we're going to have another expansion of our range, then the statistics are going to get better, and those are things to watch. I'll close the talk with the last 5 minutes about the future, and this picture I put up is not from a gravitational wave detector. It's from the LISA Pathfinder mission, which the European Space Agency launched to test the LISA technologies, test the technology particularly for isolating masses in outer space and keeping them really quiet so that there's no disturbance on them, so that when LISA is flown, it's really measuring test masses in free fall. And so this was an experiment to guarantee free fall. It did it extraordinarily well. The horizontal scale is a frequency spectrum, so this is a power spectrum of the disturbances, basically. The vertical scale is a measure of the displacement, so it's the square root of the power spectrum, the displacements that have been measured in accelerations to measure, not displacements, but accelerations in meters per second squared. And near the top, you see a little notch which says LISA Pathfinder requirements. That's what ESA said it wanted this spacecraft to do in order to be regarded as a success. That's where it had to be, below that notch. Well, you can see that this mission got way below, and after they'd analyzed the data and taken into account, they were way down in that red region. The other white curve is the LISA requirement. To fly LISA and successfully detect what LISA's been promising, you have to have disturbances below that white line. Well, on the very first go with this test mission, they were able to get disturbances that were factors of 2 or 3 below the LISA requirement. That's an astonishing quality, and because the European Space Agency was so pleased with this mission, not only because of the return of the science measurement like this, but also the fact that it had no problems. There were no backup systems that needed to be invoked or anything. It just worked out of the box. They approved LISA, and LISA is now being built. So I wanted to, that's the Pathfinder, that's the future, one of the future directions for our science. But first of all, let's talk about the immediate and near and middle term. Observing around O3b ended just as the pandemic was beginning. The data will be coming out soon. There's a lot of analysis has been done. Kagra joined the network just at that time in Japan, and the Japanese detector. LIGO, Virgo, and Kagra are planning 04 after June of next year. It's been delayed a bit, but not very much by the pandemic. And Virgo should have a big increase, but also will be, the LIGO detectors will be will extend their range, as I mentioned before. 05, the one after this, 04 will take a year. We'll shut down and we'll do an upgrade that's called A+, Advanced LIGO Plus, and then start 05, maybe 2024. That's another factor of 1.5 or so in range, which you cube to get a factor in volume. LIGO India is being built to A+ sensitivity, and so sometime around that time, we're hoping that LIGO India will be able to participate as well as Kagra you will get that better sky coverage, and we'll get a better glitch rejection. I haven't talked about that, but networks reduce the amount of confusion noise you get. Gets you down to the level of pure Gaussian noise limits. What science is coming? Well, the event rate will be more than one a day typically, and we're expecting information about stellar evolution, dynamical binary formation modes, that is in globular clusters, for example, or in triple systems. We're hoping to get a lot of information about the nuclear physics of neutron stars through their equation of state being pinned down and so on. So there's some fundamental physics coming out from that. We'll expect maybe to see gravitational lensing in gravitational waves themselves, and that could be interesting also for H0 measurements. We hope we will detect gravitational wave pulsars, spinning neutron stars with some deformation, radiating continuously. And I haven't talked about that, but we're looking intensively for those. We still haven't found them from any of the neutron stars that we know, or any neutron stars that may not be out there that we would only be able to detect this way. There are exotica that we'll be looking for, primordial black holes, cosmic strings, and so on, and the fundamental physics. So deviations from Einstein and all of that. So there's a lot of physics coming up with this next development in detectors. The Hubble constant, I talked about it earlier. I just want to say where we are now. This diagram shows, is a scatter diagram of the measurements of the Hubble constant as a function of time. So the horizontal scale is just years from 2000. The vertical scale is the value of the Hubble constant. And you can see it was very poorly determined, even in 2000. But now, if you just look at the right-hand part of this, you see that there's the blue dots are grouping together, and they have very small error bars. Those are the measurements using supernova type 1a standard candles. And then there's the red square, which also has an error bar that's smaller than the size of the square. That's the CMB measurement by Planck. And they're different, by differ from each other by almost 5 sigma. There's also this purple diamond. That's the H0 measurement that we had from the one event, and we're not contributing, of course, to this. But the real worry is that we have 2 values that ought to agree, and they don't. This is called a tension, but it's becoming a real concern. If it's real, if it's not a systematic problem with the measurements, then there's some new physics that's needed, not necessarily completely new theories of physics, but something that's being left out of our understanding of the evolution of the universe. Maybe new particles of something, but to resolve it would need new physics. But the question is, we don't yet know. And my worry is that all of these methods need to model something to do the calibration. The standard candles are complicated systems. We don't really know. There are other standard candles that people are starting to talk of, like tip of the giant branch, which are giving different values. So how are they being calibrated? Even in the CMB, there's a calibration step, or there's an input of a physical measurement, which is the speed of sound at the time of decoupling, and that could be affected by, it could be changed if you change the physics of the early universe a little bit. So the systems are complicated. The story is the systems are complicated. Our dark siren, our standard sirens are not complicated. Our standard sirens ought to give us reliable numbers if we get enough statistics. And our dark sirens, the dark sirens are the ones that are black holes, because there's no kilonova event. You can't get a counterpart. You can't just place them in a galaxy like we did with the kilonova. You have to do a statistical analysis over the sky. That's something that I explained how to do in the original paper in 1986 that I published on this. And we're looking at that now for 04, because we're expecting in the year of 04, maybe 250 dark sirens that could be used. And instead of having just a couple of events, we are suddenly going to be in a system where we can average over the errors of individual events. And I think it's very possible that we can get to the 2 or 3% accuracy level, and that would be enough to place us somewhere in that diagram that would be illuminating. You can take your pick. If we wind up on the blues, then probably there has to be new physics to reconcile these two. If we wind up with Planck, or somewhere in the middle, distinct from all of them, then there's probably something to do with systematics. So we have to wait and see. Maybe 3 years from now, we'll have done the analysis and we'll be able to make a statement about that. That's very we're hopeful that'll be an outcome of 04. We can even do better when we get to A+. We could probably get to 1% after a couple of years of A+. So by the middle of the decade, or let's say 27 or something, there'll be even stronger statements coming out. So now this is the last slide, taken a bit of extra time. LISA, as I said, because of the success of LISA Pathfinder, has been approved for launch in the mid-2030s. LISA has an enormous range for the kinds of binary black holes that it's looking for. For some systems, it can go to very high redshifts, I'll show you in a minute, and go through the epoch of reionization. Reionization blocks optical observing at around redshifts of around 10 or 12 or something like that. You can't see beyond that, but that doesn't affect, gravitational waves aren't affected by that. So it'll be a probe of individual systems at very high redshift for the very first time. So there's lots to come from LISA, and I'm very excited by that. And we're also not yet approved, but on the drawing board and as proposals, we have ET, that's the Einstein telescope, that's the European project, and Cosmic Explorer, that's the American project, which are called third generation ground-based detectors. And we expect those to arrive. We hope they'll be funded by, sometime by the end of the 2030s, a bit after LISA. And they will go right out to the edge of the visible universe. So those are the detectors that will really be gathering all there is to be gathered. There's a number of papers there on the archive if you want to look at white papers, and also there's a paper by GWIC, the Gravitational Wave International Committee, about the 3G. That's on the archive, but it's also in Nature Reviews of Physics. This is the last picture I'm going to show you. It compares ET and LISA. They have different frequency ranges, so, which translates into different sensitivities to different masses. So the horizontal scale is the masses of the binary black holes that they would be detecting. And ET would be in the range of, let's say, 1 to 1,000, and LISA in the range of, let's say, 1,000 to 10 to the 8 in this. And what the vertical scale is the redshift at which they can make detections. These are enormous. These are incredible redshifts. And the coloring is the signal noise that they can return. So if you look at LISA, the light green is 200, a signal noise ratio of 200 for amplitude. For energy, that you square that, that would be 40,000 photons of signal for every one of noise. That's the kind of accuracy that LISA will have, even at a redshift of 20, if the source is at a redshift of 20. And ET will go out to redshifts of 20, at least with signal noise of 20. So we're going to be looking at things we never had access to before with these kinds of with these new systems, and I think it's a very exciting time. We're just beginning, and so I'll leave you with that thought. We're just at the start, and I'm happy to take questions. And I'm sorry for keeping you very too long if you had to leave, or if you feel you have to leave, please do.
So, Professor Schutz, I mean, it has been a wonderful webinar. And before we proceed to the questions, I'll ask, as traditional being done here, ask everybody to turn on their microphones for a huge round of applause in retribution for Okay.
Thank you very much. Thank you. Thank you.
Yeah, because I mean, this applause is good because you have the feeling sometimes that you're talking to an empty room, but
Yes,
you
that's
have
right.
more than 100 people if we count together the people that are inside this virtual room and the people from YouTube. So we already have some questions, but before that, let me give you an overview of the audience you had. I'll try to be brief this time. But first of all, I'd like to mention that we have people from all around Brazil, north to south, west to east. So we have people from all 5 different regions of Brazil, states like Amapá, Pará, and Tocantins of the north region, the northeast region. We have Maranhão, Paraíba, Piauí, Rio Grande do Norte, Sergipe, Center-West region, where the capital of Brazil is. We have people from Brasília. So we have people from Southeast, obviously, Minas Gerais, Rio de Janeiro, São Paulo, and also people from the South region, from the states of Paraná and Santa Catarina. I know these names are different to you, but I mean, it's just to register the wide Brazilian audience that you had. Right. Well, we have from the Pará state where you're organizing this webinar. We don't have people only from the capital, Belém. You know, the Pará state is bigger than some countries in the world, right?
Yeah,
so
right.
We have people
right.
from the cities of Ananindeua, Bragança, Capitão Poço, Castanhal, Marabá, Santarém, and so from Brazil, I mean, we have people. We have undergraduate students, graduate students, teachers, postdocs, technicians, professors from many different institutes, universities, centers of research, and observatories all around Brazil. So, but we are not only with people from Brazil, right? We have also people attending you from Mexico, from Chile, from Portugal, and from London, very near to you. Okay, so let us then, with no further delay, move to the questions. So the first question was registered by Satish Kumar, VH, that speaks from Rio de Janeiro. Satish, do you want to turn on your microphone and make the question yourself?
Yes, Luis, thank you very much.
You're welcome.
Thank you, Dr. Schutz, for the wonderful talk, especially the first part where you showed several expressions in terms of Newtonian potential, right? So I wonder, are those post-Newtonian approximation equations?
Yeah, those are not exact. Those are the lowest order Newtonian approximation. Yeah, that's right.
So following that, what would be the highest order of post-Newtonian approximation you would require in order to compare with the experimental data?
Well, to detect them, we usually just need the lowest order because we have the waves coming in that we can observe when the systems are well separated and the velocities are well below the speed of light. But to get information out, then we fit, once we've detected the signal, we go back to it and we fit waveforms that involve the taking out lots of post-Newtonian effects. And that's how we extract all the information. We have fits that, we have waveforms that go up to third post-Newtonian at the moment, I believe. I think not complete at third, but they do have some of the most interesting effects that we're looking for. And there's a program to try to do better than that, to try to go higher.
Great. One quick last question. What do we learn from multiples beyond quadrupole other than the inclination?
Well, we learn the masses, the individual masses. That's the most important thing, and that just comes from the first 1.5 post-Newtonian. It's the very first step, and then sorry, that's it's the very first. It's second post-Newtonian. It's the very first step in the conservative part. But then we have spins as well, and just as in electromagnetism, where you can have spin-orbit coupling, which is important for the spectra of atoms, where the spin of the electron couples to the angular momentum of its orbit, you can get spin-orbit coupling in gravity, where the spin of a neutron star couples to the angular momentum of its orbit. And you can also get spin-spin coupling, where the two neutron stars or the two black holes each have spin, and they couple. And what is most interesting about that is when the spins are not aligned. If one of the spins, let's say, of a neutron star, if it's actually spinning about an axis that's in the plane of its orbit, then you can get very large precession effects toward the end of the orbit. And so these things that are higher post-Newtonian, they become very visible. They make changes in the phase that are very measurable. One of the things to remember is that the post-Newtonian says at any one time these effects are small by some power of V over C. But when you're looking at a signal over a certain amount of time, changes that are produced in the phase can accumulate. And so a small effect can become much more measurable. And that's what happens with a lot of these spin effects. If you found a system with odd spin arrangements, like the spins are not aligned with the orbit, that would argue for a system that was where the two objects were formed independently of one another. They don't have a common history, and they just formed a binary system with the assistance, let's say, of a third body in a three-body interaction. And so there shouldn't be any relationship among the spin directions. So there's information like that we're looking for intensively.
Okay, so thank you, Satish, for your question. Thank you, Professor Schutz, for your answers. And let's move now to the next question. Before that, I asked the people from the secretary to take care of the microphones. I suppose that there's some microphone turned on. Okay, thank you very much. So let's move then to the next question. So it comes from Vitor Sampaio. Vitor, do you want to make the question yourself? And if so, please let us know from where are you attending this webinar.
Sure, I'm here in São Paulo, and I'd like to know how gravitational waves can constrain inflationary models.
Yeah, I didn't have time to talk about gravitational waves from the Big Bang, and of course, so I'm very glad you've asked this. Gravitational waves ought to come from the same sorts of perturbations that we have seen in the cosmic microwave background, the sound waves that create the small fluctuations in temperature that Kobe and now the Planck satellite have been able to measure so accurately. They should also create gravitational waves. And so if we can measure those gravitational waves, we get our earliest glimpse of the universe. So when I say created, they should be associated with gravitational waves, because the gravitational waves were created at the same time as the fluctuations themselves. The fluctuations began quite close to the Big Bang at the end of inflation, and not at the time that the cosmic microwave background was being formed. So we're looking back. If we can get those gravitational waves, we're looking back right to the end of inflation. And so the spectrum, for example, would be extremely important for understanding the physics of inflation. But the predictions are that the random gravitational waves that we might observe today with our detectors would be rather weak. And we do look for them, but we are not surprised that we haven't found them yet. Maybe we would find something, but maybe we wouldn't. There's a better chance for seeing them actually in the polarization of the microwave background, and the current ground-based radio microwave telescopes that are looking at the CMB from the grounds, from the South Pole and from the Atacama Desert, are many of them looking explicitly for the signature of gravitational waves in the microwave background itself, how the waves have made an imprint on the microwaves at the time that the microwaves were becoming free. So that would maybe be the best way of detecting them, and it would be very exciting if we can get that kind of information. It would constrain, for the first time, it would really constrain, be a direct constraint on the parameters of inflation.
Okay, thank you.
Thank you, Victor, for your question. Thank you, Professor Bernard Schutz, for your answer. Let's move to the next question that comes from Igor Mo, who is a PhD, sorry, is a master student at Rio de Janeiro. Igor, do you want to make the question yourself?
Oh, yes, please. Thank you for your great talk. I would like to ask two related questions. What are the experimental prospects for detecting the gravitational memory effects associated to the action of the supertranslations, the abelian infinite dimensional proper subgroup of the BMS group, which is the extension of the Poincaré group discovered by Bondi and his collaborators, which are believed to act non-trivially at the radiative phase space at null infinity, say Scri plus, as proposed by Andrew Strominger and his students as a result of their deep relation to an old result from quantum field theory, the Weinberg soft graviton theorem. So
yeah. So shall I answer that now? It's a very interesting effect to look for. It is predicted by general relativity, and the problem with the memory effect itself is that it's a very, very slow thing. It's almost like a DC kind of thing. It's a very low frequency change in the gravitational field. So our detectors are not going to respond to that directly. So there have been people who have talked about different ways of doing it indirectly. I'm not an expert on that, but basically, I think the best chance comes from systems like we've observed, where there is a big change in the mass of the system. So much mass is radiated away in gravitational waves. You know, a good fraction of the mass, several percent, 3%, 5%. And if we can get some gravitational waves from before and from after, so we get ring down radiation from afterwards, and if we can measure them with very high accuracy to see the slight effects that might be associated with the fact that these waves have some waves have come out before the memory and others after, then that may be our best handle. I think that would have to wait for the third generation, maybe Lisa, because you need very high signal to noise to do those things. There may be other ways that people have talked about that I'm not aware of, but because, as I say, I'm not expert on that. But unfortunately, for the current instruments, it's not something that we can directly detect because it's so low frequency.
Okay, As a follow-up question, which is a little bit more speculative, there are many authors, such as Glyn Barnick from the Solvay Institute, proposing to generalize the BMS group to a Virasoro group, such that the central charge is proposed to be the generator of superrotations, manifesting themselves as spin memory effects. As the latter requires a Sagnac-like detector, would this be possible with the forthcoming Einstein telescope? Or do you believe it is even measurable in principle? That's my final.
I wouldn't say it wouldn't be measurable in principle because yeah, the angular momentum, the spin, is one of the things that's very clearly doesn't obey the rotation, the symmetries of the rotation group that we're used to in flat space time. So that is, if you have a radiating space time, all of that goes out the window. And so, yeah, I would say it's a physical effect, and therefore I would never exclude that it would be possible to measure a physical effect. But ET will have a Sagnac mode. The problem is that ET will consist of there will be no signal traveling directly. There will be no optical signal traveling directly around the triangle. It's triangular, but it has 3 interferometers in it. so you would have to be very careful about monitoring the phases in order to get a Sagnac mode. You could do that. LISA knows how to do that. LISA also consists of a non-standard kind of interferometric setup, but it knows how. We know how to monitor the Sagnac mode with LISA as well. So if it requires, which I'm not aware of, but if it requires a Sagnac detector, maybe those would be able to do it. But if it requires something like comparing 2 different Sagnac detectors, then I don't see how we're going to be there very soon.
Okay, thank you for the honor. And to finish, let me say that your textbook on geometric methods was a path changing for me when I was an undergraduate student. So it was an honor to talk to you. Thank you very much.
Okay. Thank you very much for that.
Okay, thank you, Igor. Thank you, Professor Schutz. Let's then move to the next question that comes also from Rio de Janeiro, this time from Professor Maurício Calvão. Maurício, do you want to turn on your microphone and make the question?
Yes, it's already turned on, Crispino. Thank you very much. Well, I would like to thank, first of all, very much Professor Bernard for this enlightening and very dense webinar. And my questions are all related somehow to modified gravity models, theories. And I might sum them up as asking you to tell us something about the potential for detectability of other polarization modes in these modified gravity theories. And also, the second question would be, how does the scale freedom you mentioned, which prevails in GR, in general relativity, how is it modified, if at all, in these alternative gravitational theories?
A lot depends upon the theory.
Such as perhaps f of r, if
clearly scaling is broken if you introduce let's say a coefficient that has let's say an extra term in the Lagrangian. a coupling constant. And so if you so one way of looking for those is to look for the scaling to be broken. The effects are usually too small for the current generation of detectors, but the fact is that we have people inside the collaborations which are looking at our data entirely from the point of view of testing GR in all sorts of ways. So yeah, the scaling is one thing that breaks at some level. The classes of theories that still obey the equivalence principle are harder to separate from general relativity usually than those that don't. But one of the things that the things that are easiest to detect are things that accumulate with time, because these are small effects. You want this accumulation effect to happen. A classic one is do gravitational waves travel at the same speed as electromagnetic waves? And we were able to determine with the binary neutron star, the electromagnetic waves from the gamma ray burst arrived 1.7 seconds after the end of the gravitational wave burst had arrived. And 1.7 seconds over a distance that's travel time of over like 120 or 130 million years is an extraordinary equality. So it gets you to 10 to the minus 14 or better, I suppose, in terms of the speed of light. So that one event was an extremely good test, and I should say it's not that we expect those to have been the same. We expect the electromagnetic waves to come out after the merger signal finishes. The gravitational wave is the first thing that happens, and the merger signal finishes just when all the nuclear physics is just starting. And so had the gamma rays come out 1.7 seconds before the gravitational waves ended, we would have said that's a violation. The light is traveling faster than gravitational waves. But the fact that it's 1.7 seconds is just about right for the hydrodynamics that's expected. And so it's consistent with there being zero difference between the two. So that's a pretty strong test. Another test that we are beginning to be able to make is birefringence. Again, the propagation of gravitational waves, do the two circular polarizations that you can decompose any wave into, even a linearly polarized one, the two left-hand and right-hand circular polarizations, do they propagate at the same speed? If they don't, then they will get out of phase with one another when they arrive, and our signal models, which are phase, follow the phase completely, would just be all over the place. So signal models wouldn't fit at all. Again, you can put limits on that. I can't remember what the limit is, but from all the systems we've detected, we've detected signals that are that come from redshifts of 0.5 and higher, traveling there for a very, very large distance, and they still seem to be coherent in terms of the phase evolution that we expect. So again, the birefringence seems to be, if it's there, extremely small. I'm not an expert on all the different kinds of things that we might be able to test, but there are teams in the collaboration who look at this very intensively, and I'm sure they're testing for whatever they think is possible at the moment.
Okay. Thank you.
Thank you, Mauricio, for your questions. Thank you, Professor Schutz, for your answers. Let's move then to the next question. Questions were very much concentrated in the southeast region of Brazil. Now let's move to the northeast, to the state of Paraíba. Paulo Rodrigues da Silva. Paulo, do you want to turn on your microphone and make the question yourself, please?
Sure, Crispino. Thank you. Thank you, Professor Schutz, for this beautiful talk. I'm interested in one of the consequences of the discoveries with these gravitational waves, which is related to these supermassive black holes. I would like to know if you have something to say about the implications for the dark matter scenario, since till now, almost everybody believed that dark matter was basically composed of a new kind of particle.
Well, yeah, the two things that you mentioned are a little bit separate. We're not, of course, directly dealing with supermassive black holes here. Lisa will be observing black holes of mergers of black holes of 10 to the 6 solar masses and higher, which is, you know, and those are systems in which dark matter probably played a bigger role in forming them and so on. But there are also suggestions that the binary black holes that we're seeing are part of the dark matter themselves, that the dark matter isn't composed of little particles, but it may be at least partly composed of constant, you know, of these primordial black holes that have grown to the size of 30 solar masses or whatever, the ones that we're detecting. That's a viable scenario. Some people are pushing that quite hard. I think as we get better statistics, we have, particularly from the next observing one, we'll be able to say something about that scenario. But if there are too many of them, it becomes difficult to reconcile with other bounds that you get from other parts of astronomy, for instance, from microlensing and so on. So it's an open it's definitely an open question at the moment about whether our binaries are part of the dark matter. But I'm not sure that that's what you had in mind when you mentioned dark matter.
Yes, I was thinking, since dark matter could be composed, at least a tiny part of it, of the amount of black holes in the universe, since you are discovering that there are black holes which are much more massive than believed, I'd like to know if this can have some implication for the dark matter.
Maybe, Professor, he's mentioning the intermediate mass black holes that you've been talking about.
Yeah, I mean, it's been very hard to get a handle on intermediate mass black holes, and it still is. It is possible that they are a major component of the dark matter, that the black holes of different masses in different mass ranges are a major component. I wouldn't say the fact that we're observing them proves that, because the fact that they were unexpected was something I said rather a couple of times, but because I didn't have enough time to stop and explain what I meant by that, is I'll use this to clarify that statement. The fact that they were much more massive than we had expected. When I say we, I really mean the standard astronomical community. In fact, it was before the first detection, many astronomers, perhaps a majority, believed that there would be no binary black holes at all. And that was based upon studies of the evolution of binary systems that would eventually form binary black holes. They would start out as two massive binary two binary stars with very high mass, and when when you get to the phase, one of them has formed, let's say, a compact object, maybe one of the black holes. The other one becomes a giant. The theory was that if they were eventually on their way to form a binary black hole, when the giant expands, it would expand further than the distance to the companion. And so you'd have a common envelope. You'd have both objects inside the envelope. And so that companion then, would, by friction, would barrel together down into the center of the giant star. And you'd get what's called a Thorne-Zhidkov object, a single object, not a binary, not something that radiates gravitational waves. That was the received wisdom. There's nothing wrong with that picture. It does seem to happen. It does seem maybe that will happen in binary stars that are forming today. But there were already, before we had the observations, there were already groups of astronomers who had pointed out that this is very dependent upon the metallicity of the cloud of gas. And if you take low metallicity clouds, the common envelope phase is totally different, because the low metallicity means low opacity, and the density of the envelope is way lower. The friction is lower. The stars do not merge together in that way, and you get formation of binaries, even massive binaries, depending upon how massive the protostars were. So there were predictions that there would be binary black holes, and what we've seen is right. So is binary black holes. So that means that if they were formed by stellar evolution, the ones that we're detecting, they came from low metallicity clouds. That doesn't necessarily mean very early in the universe. You can look around our own galaxy and find places where stars have formed. They're called Wolf-Rayet stars from low metallicity clouds. There's not uniform mixing in the galaxy of all the metals, and so the population of binaries that we're seeing could be just the stars that formed in low metallicity clouds. And I think that's the conservative point of view. But it is still an option that maybe there are primordial black holes, yeah. And that would be part of the dark matter then.
Okay, thank you very much, Paulo, for your question. Thank you, Professor Schutz, for your answer. And then let's move to the next questions. So we still have some questions here, Professor. So you tell me when you would like to stop.
Yeah,
okay?
I should be finished by about 1:15. I have other commitments.
A quarter to, or
a 1:15. So shall we say another 5 minutes? Yeah.
Okay, great. So let me move then to the next question from Isabela Matos. That is a PhD student from University of Rio de Janeiro. Let me just say that many people in the YouTube are making compliments to your very nice talk. I should mention one of Isabela's supervisor, Professor Yoav Vaga, and also Nadia Magalhães from UFPA Diadema, São Paulo. Isabela, please go ahead and make your question.
Thank you, Professor, for your talk. It was written in one of your slides that what one measures in an interferometer is not exactly the energy emitted by the gravitational wave, but H, the waveform. Is it also true for gravitational wave stochastic backgrounds? And isn't H a gauge-dependent quantity? This is my first question.
Yeah, so the gauge-dependent quantity, yes. What we mean when we talk about the H in a gravitational wave interferometer is we actually mean the strain in the arms, the separation in the arms, and that of course is a measurable thing. Then to translate that back into the amplitude of the gravitational wave that's coming in, you do have to choose your gauge. We always use, for that gauge, we always use what's called the transverse traceless gauge, and H there is a well-defined quantity. So yes, it's gauge dependent, but in the end, what you have to do, whatever gauge you're in, is you have to say, how does this gravitational wave affect my interferometer? What is the measurement coming out of it? And that's the thing that's not gauge dependent. It's going to be the same, whatever gauge you use. So that's the gauge dependence. The question about the energy and stochastic, yes, for the stochastic background, what we look for is a correlation of the output of two detectors, and so we do multiply the data from the two detectors together, and that produces something that has more has the dimensions of energy, and so effectively then we're measuring the common energy in the gravitational waves. Yes, but when we're looking at a single detector, the output is just the strain, and that's the amplitude.
Okay, thank you.
Isabella. Well, I mean, if he said a quarter to, so we are right on time. Okay. So I will I will apologize all the people that have questions here, like Cecilia Quirente and also Odilio Aguiar, that is part of the LIGO team, also works in Institute for Space Research in Brazil, is saying hi. And Professor, maybe you just will take this last minutes you have with a closure, let's say, telling us things that you would like to spot out, I mean, to emphasize in the next, let's say, years to come in gravitational waves, and even also tell us a bit about what should we expect of this new edition of this first course in general relativity, your book that is going to be released in the next few months. So, please, Professor.
Okay, I'm very happy to talk about my book. It's an update of the edition that appeared in 2009, and it'll contain a treatment of the detections that we've had so far, but also a lot of new material on the astrophysical background of these detections, and there's a new section on how we do the data analysis, and also the cosmology has been totally redone. Cosmology is now a high precision science, and it wasn't treated that way in the first version of the book. So the cosmology chapter is data first, and it's a totally different perspective. So yeah, I hope that it's therefore a modern book and will stand the test of time, at least for a little while. Regarding what's coming in this field, well, I suppose what I would say to people, it depends upon whether you're a theoretical physicist or an astronomer, or you're actually working on gravitational waves. We need as many people as we can working on gravitational waves, getting these projects, getting the data. The data is going to be enormous. So getting ready to spread the data analysis. Already the LIGO scientific collaboration is a worldwide thing. So we certainly could use more people involved in the long run. And when Lisa comes along, there'll be an enormous amount of data. If you're a theoretician, there are problems about Lisa that we really need to solve. If you're a relativity theorist, we need good signal models for extreme mass ratio binaries. That is, binaries where the inspiraling object is maybe a 10 solar mass black hole or a 30 solar mass black hole, and the central object is 10 to the 6 solar masses. So maybe a mass ratio of 10 to the 5 between them. That is something that all our post-Newtonian expressions cannot faithfully keep up with. The errors accumulate too fast. There's a worldwide research effort going on in modeling those systems, but it's showing things in principle that it can do, but mostly for Schwarzschild black holes or for Kerr in equatorial orbits. We don't have very much for Kerr general orbits around Kerr. And, there are wonderful issues of resonances in the inspiral orbits where things seem to be extremely sensitive, maybe chaotic. So there's a lot of physics in those orbits, which will, and they will test the Kerr geometry enormously well. If you're interested in testing, then those are the ones that are, I think, going to be the most important, because we'll have 10 to the 5, 10 to the 6 cycles of radiation from these systems. We'll have very high signals to noise. So I would say, if you're interested in, if you're a theorist and you're interested in looking for problems to work on in gravitational waves for the future, then Lisa is presenting a lot. The Lisa community is an open one and has teams on cosmology, teams on equations of motion like this, and signal construction, signal models and things. So there's lots to do there. And if you're an astrophysicist, it's multi-messenger. I think we're going to be getting very interesting joint observations with telescopes like LSST, the Vera Rubin Observatory, and with radio telescopes. So I think the chance and the opportunities for multi-messenger astronomy, the opportunities for preparing for the next generation, the next set of detections. For example, we need galaxy catalogs. We need galaxy catalogs. We need catalogs of galaxy clusters that are reasonably complete out to redshifts of 0.3, 0.4, in order to be able really to exploit all the data that we're going to get and be able to associate some of the dark sirens with galaxy clusters and so on. There's a lot of information there if we can get enough information about the galaxy clusters. So yeah, there's plenty, I think, of interesting things that I would encourage people to take an interest in, and also, just to be ready for when the data starts coming in again.
Okay, Professor, we thank you very much for this wonderful, complete, this very wide panorama that you have given us of the past, present, and future perspectives in gravitational waves. And in retribution for this wonderful talk, I'll ask everybody to turn on their microphones once again for a final round of applause.